Hi, I'm Gordon Matthewson from the University of Colorado Boulder. Changing the context in which you experience pain, for example by focusing on how pain is not necessarily harmful to the body, is known as cognitive self-regulation. We've known for a long time that changing the way that you think about or appraise pain has large impacts on how it makes you feel. However, it's less clear whether this also impacts the way that the body responds physiologically to pain. In this experiment, we trained 41 healthy participants to regulate their experiences of heat pain on their arm up or down using mental imagery. So for example, we asked people to imagine that they were outside on a very cold day and that this heat was warming them up or that it was scalding their skin. While they did this, we measured their electrocardiogram activity and their skin conductance responses.
Hi, this is Choong-Wan Woo from Choong-Wan University in South Korea. Because both pain and cognitive effort can influence heart rate and skin conductance, the impacts of regulating pain on pain-related physiology could be masked by the mental effort or cognitive control-related physiological changes. Here I'm showing the physiological responses to different levels of heat stimuli. And just like we'd expect, skin conductance response and heartbeats increase as temperature increases. So using the trial-by-trial physiological responses, we first created an average physiological response for each participant to each of the 6 temperature levels they were given. And using those average physio data, we trained the model using principal component regression, where we use principal component analysis to reduce the dimensions of our physiological data first, and then use the small numbers of components as the regressors to predict the averaged pain ratings for each temperature level. This regression model was projected back into the time space, yielding canonical time series of physiological responses predictive of pain. So we can call this temporal profile of predictive weights as physiological markers for pain. And the more participants' physiological response to heat resembled this pattern, the more pain they were likely to report. Importantly, this training physio data was taken from groups of trials where participants were instructed not to regulate pain but experience it passively. The x-axis here represents seconds, and the orange bar along the x-axis indicates when heat was applied. The y-axis shows the magnitude of the predictive weights. Higher predictive weights indicate that if you have higher physiological response during this time duration, the model will predict higher pain. So this SCR model basically suggests that after you received painful stimuli, if your skin conductance level is lower during 3 to 8 second period and higher during 12 to 20 seconds period, you are likely to feel more pain. And the ECG model suggests that after you receive painful stimuli, if your heartbeat is faster between 7 to 13 seconds and slower after 15 seconds, you are likely to feel more pain. The predictive performance of these markers was quite good. The correlations between predictive versus actual pain ratings ranged from 0.65 to 0.82 from the leave-on subject out cross-validation. Also, to test the specificity of these markers for pain, we tested our SCR model on another independent dataset where some participants received pain and the rest of the participants watched their romantic partners received pain. As you can see in this figure, our marker responded strongly to actual pain but responded less when observing pain.
Now let's take a look at the results of the effects of cognitive self-regulation on behavioral and physiological responses. As you can see in this figure, regulating pain down causes less pain to be reported, and regulating pain up causes more pain to be reported. These effects of regulation correspond to about 1 degree of temperature difference. In other words, regulating a 47 degrees Celsius stimulation down feels about as unpleasant as a 46 degree stimulation that you don't regulate. When we tested our physiological markers for the effects of cognitive regulation, we found that they were indeed reliably impacted. Compared to the effects on pain report, the effects of cognitive self-regulation on our physiological markers were smaller, but still significant. Instead of 1 degree Celsius, they impacted our ECG marker by about 0.4 degrees Celsius and our SCR marker by about 0.22 degrees Celsius. We think that there are several major implications of this research. First, it's been a challenge for clinicians and researchers to find physiological markers for pain. Here, we show that predictive modeling has potential to develop physiomarkers for pain, and we provide an example of one potential physiomarker for acute experimental pain. Second, this study showed that cognitive self-regulation operates on the level of the autonomic nervous system, producing physiologically meaningful changes instead of reducing pain through behavioral changes such as reporting bias. We think that this has a powerful message for physicians and caregivers and for patients. Thanks for watching, and don't hesitate to reach out to our corresponding author, Dr. Tor D, with any questions.